everybody. My name is Shingai, and Flora and I are going to be working through this tutorial. So this is the PowerPoint version of a model that Flora just took us through. If you haven't seen the model video, feel free to go look at that. And we also encourage you to run the model for yourself. So once again, this is a non-technical course, but we do include the actual model so that you can have a hands-on experience of what it's like to build a natural language processing model. So Flora is going to take us through the actual core of the assignment. And then after this, you should be in a position to start your assignments. So Flora, over to you.
Thanks so much, Shingai. So this is just going to be a quick overview of sort of the same things we talked about as we went through the code in detail. And like Shingai mentioned, this is just to set you up on your assignments. So you understand sort of how it works end to end and what types of evaluation questions we're looking at for you to answer. So just to take a step back, when we talk about natural language processing, we're talking about this in terms of the idea of artificial intelligence and the way the way computers can interact with natural language, the way that humans would normally speak and write. And so the main goal of NLP is to understand or to generate natural language. So in this particular assignment, we're going to focus on understanding language because we are going to make predictions of diagnoses based on medical notes. But the evaluation part of it, you can kind of start getting a sense of like, oh, maybe we can actually use some of this technology to kind of generate text, generate language as well. So you see at the end when we have the evaluation, sort of the scenario that we're asking you to look into and to get the understanding of that. So there are many examples of NLP applications, and I'm not going to go over all of these, and you're probably familiar with most of these examples. But in our case, for this particular assignment, we're going to focus on text classification. So we're classifying the diagnosis of a patient based on medical notes. So the underlying main technology or algorithm that we're using is called transformers. And the reason why we wanted to bring this into natural language processing, into the natural language processing module is because this is now the state-of-the-art algorithm that's used for natural language processing. And you don't need to understand sort of technically how this works, but the idea is that is using the idea of attention. So if you think of it in terms of a sentence, when you look at a sentence, what do you pay attention to? You know, how do you associate certain words with, let's say, she went to the mall. So you know that she is referring to a person and a mall is the place. And then the sentence can be longer. You know, she went to the mall and bought, you know, her dad, you know, a sweater, and it was great. So like a sentence can be very complicated. So the power of transformers is that it doesn't just look at one word or two words at a time. It actually looks over the entire sentence and figures out the context. So this is algorithm that got really popular, you know, even just, you know, 3 or 4 years ago, and you can imagine how fast this whole field is changing. But it has really helped make the whole area of natural language processing much more robust. And so that's why we're talking about transformers, just so that you can have some of this terminology and understanding when someone talks about it. And BERT, sometimes you might have heard people talk about BERT, you know, could not really relate it to the Sesame Street character, but this is just sort of a data science programmer humor. But BERT actually stands for bidirectional encoder representation from transformers. So if you think of this whole thing, you just think of this whole thing as a transformer algorithm. This first part is BERT. This first part is the encoder. So when we say encoding, what we mean is that we want to take all of this text information and translate it or transform it into a way that a computer understands, which are, you know, numerical vectors. And so that's the whole idea of BERT, is that it was pre-trained on Wikipedia and a whole bunch of books so that it starts to understand language context, and not just individual words, but actually the context of grammar and parts of speech, and what words might relate to each other, what to pay attention to, all that good stuff. So that is why we are using BERT as sort of our base to train our model, so that we are already get a head start in understanding our medical text. So in terms of the model process, as we mentioned, we start with the medical reports, and under each of these blocks, you see sort of the individual activities or actions that we're taking related to this. So first, we're importing all of these medical reports, as well as the labels or diagnoses associated with each of the reports. And then we're going to do some processing to parse the text. And if you watch the coding video, you hear me talk about tokenization, transforming this text into, words and punctuations and all that stuff. And then we're going to take all of this data and train the model. So what we're trying to get the model to do is to take this input text that are encoded and transformed into tokens, and get the machine to find patterns within those tokens in order to make a prediction on what the diagnosis could be. And then once we have the model, we want to evaluate how well it does and predict the the performance of the model using different metrics. And then we finally evaluate the results, not only from a technical perspective, but also from a clinical perspective, which is actually the goal of this particular assignment. And you'll see what we mean when we get to the questions at the end. So another reminder before you start running the code, just follow these instructions to make a small change so that your code will run faster. And the data set that we're using is a publicly available data set. It's quite a small data set of a few thousand entries, but it gives you a good example of sort of examples of SOAP notes and examples of what those diagnoses can be. And so this data set can be accessed through this link here. But when you run the code, it will actually already download it for you. So there's nothing you need to copy over. It will do all that for you as you're running the code. And so here's an example of a SOAP note. So in this example, we have a 33-year-old female with mild spells of vertigo, mild headaches, and so on. And as you can see, even within the SOAP note itself, the doctor predicted that this patient likely has hypertension. So what we want to do ultimately is to see if we can make a model that can make a prediction on a diagnosis without knowing the diagnosis, obviously. So what we want to do is, the way we think about this is that, okay, without knowing the diagnosis, can our model predict that this is an example of hypertension just using all the rest of the words in this medical note, in this medical SOAP note? So what we decided to do was that we will be within the code, we'll be pre-processing these notes to remove any reference to the actual diagnosis. Because in the end, if we're thinking about, let's say, an application where you can verbalize like the assessments, saying that, oh, this patient has mild headaches and so on. Would this AI model be able to tell you, like, well, based on what you've said, I think this is most likely hypertension. So what we're doing is that we're removing the words related to the actual diagnosis so that we can train the model to predict on everything else related to those types of symptoms. And here's another example where the diagnosis is not written particularly it's not only written in the kind of the A colon section. It's actually part of the note itself. And so in our code, we also take out references to the diagnosis anywhere in the medical text. And here's another example of a patient that has a disarticulation of the right shoulder, and another example that we will be removing it because this would be the actual diagnosis itself. So we're going to try to see if they can figure out that this is the diagnosis based on everything else, all the rest of the text in the note. All right, so now we're looking at sort of what categories we're trying to predict. So we did some data cleaning, which we mentioned in the coding example. And so these are the 11 final categories that we have that we're trying to predict. Oh, no, these are actually examples of all of the different categories. As you can see, different categories have different number of examples. There are more, there are general medical examinations and less as we go down the list. And an example of what we call an output or label or target, and we use a lot of these words interchangeably. They mean slightly different things, but in the end, we're talking about what we're trying to predict, like the class or the category or the diagnosis or outcome that we're trying to predict here. What you'll notice is that after we've done the sort of the data cleaning and collapsing some of the categories, we came up with this other category. So the reason why there's this other category is when we looked at the different diagnoses, we noticed that there are some with very few examples. And so individually, these these categories, it'll be hard for the machine to learn the patterns if they only have a few examples. So we collapsed some of those categories into this other category. So just to have a note to say that we do have this other category, and it's a bit of a challenging category for the machine to predict because all the examples in there are quite different because we combined a lot of the other diagnoses into this one. But ultimately, this is the distribution of the number of examples in each of the diagnoses or each of the categories we are trying to predict. And the training process itself, this is just a visual diagram of how a general machine learning training process works. We start with the input data, we do some kind of pre-processing, tokenization, and then we split it into the training set, the validation set, and the test set. And if you remember, we talked about the test set being a separate subset of the data that we put aside and we don't touch at all during the training process because we want this to be kind of new data that we're using to evaluate the final model. But in terms of the training process, we use the train and validation data to kind of continually train this model and track the performance. And in the example, you saw that we ran through 10 epochs or 10 iterations for the model to keep improving on itself and tweaking those parameters so that it can make a better and better prediction. So after these 10 iterations, we say, okay, we like the result. We think this is as good as it's going to get for our model. And so let's save this model and evaluate the results on the test set that we've set aside. And so this is just an example of not really the performance of the model, but this is just to show the distribution of the data within each of the training and test sets. Because, for example, if we have 11 of these categories in the training set, which is the blue, we also want the 11 all examples from all 11 categories in the test set so that we can have a proper way to evaluate how well it's predicting on each of these categories. So this is not the performance of the model, but more of the distribution or the proportion of the data within each of these training sets to make sure that we have examples, related to each category. And now we do the training. So the little diagram on the left here kind of shows the way we've set up the model. So we mentioned BERT as sort of a pre-trained model that understands language context. So we are using this as what we call a base layer. So we're taking the learning from the pre-trained models, or sometimes we call this transfer learning. We're transferring the learning from this base model in order to fine-tune it to our purpose, which in this case, we're classifying medical notes into diagnoses. And so the rest of these, layers of neural network, it's just a kind of a simple network to learn the specifics of our case, in which case the specifics of learning the tokens or the text within the medical SOAP notes and predicting the output, which is the diagnoses. And the graph on the right-hand side shows you the sort of the training progress within the training using the training accuracy and the validation accuracy. So as you can see, both training and validation accuracy increases up to a point where they're sort of plateauing at around 10 epochs. So this is where we decided to stop our training and think like, okay, this is what we think the final model should be at this point of the performance, and now we can evaluate how well it's doing. All right, so now we have the results from the training set, but we also want to make sure that the performance on the test set is comparable to what we're getting on the training set. So you remember that the test set is the subset of data that we set aside at the very beginning of the training process. So now what we can do is we can take the text, the medical text in this test training set and give that to the model. We're not telling it what it's supposed to be. We're just saying that, okay, here's some text, to make your best guess on what you think the diagnosis is. And then so the model outputs the prediction, and then we can compare the model's prediction with what it should actually be. And then this becomes our accuracy score. So now we have the accuracy score that we got during the training process as well as on the test set. And we see that they're actually quite comparable. So this would tell us that our model is actually doing quite well, even on new data that it hasn't seen before during the training process. And a confusion matrix is a really great way of visualizing the results, especially for a classification model. So you see on the left-hand side, these are what the actual diagnoses, and on the bottom are the predicted diagnoses. So using the confusion matrix, you can see how many times the model has correctly predicted the diagnosis based on each of the categories, and which categories it often gets wrong. So one example I gave was that you see here that it's often confusing embolic stroke with hemorrhagic stroke, likely because a lot of the words used in the medical text to describe stroke is similar. And again, the other category is also tricky, as we mentioned, because it's a combination of many other of the smaller categories with very different words in there. But this is a good way for you to kind of evaluate the results of a classification model and kind of look a little bit deeper into what is actually doing and what types of mistakes the model is making. We talked also a bit about the precision recall and F1 scores. So I'm not going to go into more of the technical details on how to calculate it, but basically these are scores that you can use to evaluate from a clinical perspective, how well an application like this might work in an actual clinical setting. So for example, if something has a high precision value, that every time the model is making a prediction, it's probably, going to be something that is actually the correct prediction. Versus recall, let's say if it has a low recall score, like here we see that the acute renal failure score is quite low, that means that it's only able to capture 66% of the patients that have the acute renal failure diagnosis. And for the other ones, it might be missing them. So from a clinical perspective, is that what's the risk, in an application if it's not unable to predict certain diagnosis very well, and how well do you trust it if it's not able to, correctly predict a lot of these diagnoses. So so predictions for precision, recall, and F1 scores are a really good way to evaluate, these types of classification models. And again, just to recap, F1 score is a weighted average of the precision and recall scores. It's just a way to kind of combine the two, but take into account that we don't want either one of these other scores to be too low. So it's sort of a weighted harmonic average of these two scores here.
All right, so we're now on to the interesting part of why we've done all of this great work, which is to get you involved, to get you evaluating and thinking about artificial intelligence and making decisions. So in this discussion section, I'm going to pose a few questions to Flora. and Flora is going to be in your position, and she's going to give us a reaction. So we've done this whole model where we're trying to predict diagnoses using clinical notes. Flora, do you think this is clinically relevant?
I think this would be clinically relevant if it works well enough, right? I think the difference is that based on the data that we have, it's only able to, as you can see, predict out of 11 categories. But of course, in reality, there are many more diagnoses that a doctor would be able to come up with versus this model. But the idea of it, I think, would be clinically relevant because a lot of times if a nurse, let's say, is doing a clinical assessment, they might be able to write down or speak out all the different the symptoms of the patient, but they might not immediately know what the diagnosis is. So this AI model can be a tool to make a suggestion of like, okay, based on, all the symptoms that you've told me, this could be the diagnosis. It's not to say that we are going to say 100% this is exactly what it is, but it's just the best guess. So you can think of it as a tool that might be helpful in this clinical setting.
Thanks. So folks, this is a discussion. So you come from various clinical backgrounds and settings. So you may have a different perspective, and we encourage you to please share your perspectives in the discussion, either in the in-class portion or in the discussion section of the learning management system. We're just going to get some more input from Flora. So Flora, is this, you know how it is in a real hospital setting, things move quickly, there's a lot going on. Do you think this is really reflective of actual clinical notes?
That's a really good question. I mean, I think the data that we have in this particular data set is actually pretty clean or neat. You see that the words are spelled out. They follow a certain format in the SOAP note where the diagnosis is always under the A and the description is under the S. But in reality, in a regular electronic medical system, you can imagine that physicians are always on the go. They're writing things in different ways. They're using acronyms. They're using shortened forms. So it would actually be a lot more challenging to train this for a particular institution to account for all these different types of discrepancies between the medical notes. But in this particular sample, it's a little bit simpler just to kind of show you the process. But in reality, there's a lot more that you would have to consider in terms of the data and the training process and the biases and especially with text data, all the discrepancies between different ways people describe the same thing. So I would say this is a simplified version, but in reality, it's much more complicated.
All right. So, okay, you already started answering my other question. So very quickly, removing the diagnosis. So in the original SOAP notes, the diagnosis is sometimes included in there, and you went and removed it. What was the impact on the results?
Yeah, it's interesting because when I first ran this model, I actually didn't remove the diagnosis, and it was able to predict a little bit better, obviously, because it kind of had a hint of what it's supposed to be. But surprisingly, after I removed the diagnosis, it actually did not affect the performance that much. So this is saying that the model is actually able to look at the rest of the text, so the actual descriptions of the symptoms to predict that diagnosis. So that's that's a very good point. Yeah,
it's part of that whole black box discussion about neural networks, right? Is that we don't know exactly what the model looked at to arrive at the prediction.
Yeah, exactly.
All right, bias. So tell us again where you work and why inclusion is very important to you, and then tell us what biases could be lurking in this model.
Yeah, so I work in a children's rehabilitation hospital. So we talk a lot about accessibility and inclusion and equity. And so this is a really important topic for me, and a really big topic now, really, in the whole world of AI. I think there's a lot more emphasis now on the ethical issues and the and the issues of bias. In the beginning, a lot of the focus was on the technical, parts of building a model. How can we improve the performance and all that? But now I think people are starting to think about like, well, now we have all these models, these technical models. If we are to deploy into the real world, what impact will it have on real people, right? Like, is this going to be a fair model, or is it going to pick up something that, historically has been done, but not, exactly right? So in terms of medical notes, I think a lot of that, because it comes from humans, so it has the skew of, I guess, whoever wrote the note and whoever decided on that diagnosis. So maybe, they might have a personal bias to say that, men, are more often to have hypertension. So I'm biased towards men having hypertension. And so then the model will pick up this, and every time they see the word male, maybe they'll be more likely to predict diagnosis of hypertension, which is not necessarily correct. Maybe that's just something that is historically, been included in part of the data. So I think it's really important to kind of look at not just the performance of the model, but also what data is coming in, and is this data actually making a proper diagnosis that is fair and objective across all types of patients, and not kind of specifically related to race or country of origin and that kind of stuff. So that's a really important point to consider for any AI application.
So if we were to recommend this model for a clinical setting, I think that's one of the things that I would look to include is some sort of bias testing. So, where we got those false positives or false negatives, to really dig into those subcategories to understand if there are any groups that were specifically affected by the model. And then that way we can determine perhaps some of the bias that's in the model. What else would you do to improve the reliability and usability of the model?
Mm-hmm. Yeah, for one thing, I mean, this model itself right now, it's based on a few examples. So I think getting a larger data set, and a data set that is really representative of that type of that population that you're trying to predict is really important, because ultimately everything comes from the data. Like, we can have the world's most sophisticated training algorithm, but without good data, it's not going to produce good results or relevant results. So I would definitely look at including more data, particularly data from different institutions, if this is going to be an application that can be rolled out to different institutions, because again, it has, implications with bias, it has implications with, discrepancies between how different people interpret, clinical results, or the way they write, medical notes. And so good quality data, and also to have, maybe an objective third party go through some of this data and check to make sure that the diagnosis that's associated with the input is actually something that they would agree on. Because if we train this model, we tell it to predict, this diagnosis, but, let's say 4 to 5 doctors actually don't agree, then the model is learning something wrong. So I think that second part of the kind of evaluating or making sure that the data set is actually what we're trying to get the model to learn is really important as well. And also, I mean, the third part is talking to clinicians, right? And talking about, do you actually want this? I mean, we can build the most, sophisticated technical solution in the world, but if it's not useful, then it's just becomes a good data science project. It's not something that is actually useful. So I think talking to the end users, talking to the clinicians, and maybe even talking to the patients, right? To ask them, like, how would you feel if, the doctor is using this tool, not just relying only on the tool, but using this tool to give a recommendation on the diagnosis. Like, how would you feel about this? Would you be uncomfortable with it, or would you think that, oh, this is great, it's like a second opinion? So talking to all of the different stakeholders involved, I think it would be really important as well in a clinical setting.
Yeah, so many things to consider. Just as you were talking, I was thinking, well, medical guidelines also change, right?
Yes.
You know, the correct way to put a baby to sleep was on the stomach, on the side, facing up. Over the years, there have been different guidelines that have been issued. And if we look at COVID-19, masks, no masks, 2 masks, guidelines do change. So a model like this that's trained also can't be left on the shelf and just assume that everything's okay, because the diagnosis itself could, you know, through additional learning and scientific discovery, we can actually improve on some of the diagnoses. So that's an important point. The last question here before we move on to what we need learners to do in this assignment. Bilingualism, or actually just the idea that in Canada's got so many different types of people who input the notes, who will potentially describe what they have or the symptoms that they're feeling. What implications do you think that has for the model and maybe for natural language processing as a whole?
Yeah, and this is tricky for sure, because let's say we were talking about pre-trained models before, like BERT. I mean, all of this was trained using the English language. But as you know, in a world, you know, in our world, and especially in Canada, we have a lot of different people with different backgrounds. And so I think going forward, it comes down to the data that's available for us to train, and being cognizant that, you know, if we take a lot of examples, maybe 95% of them will be in English, but the 5% that is not, we still want to make sure that this model is fair to those people and to make a correct prediction. So maybe the focus will then be on, okay, we are pretty good at training, you know, just with regular English text. So now let's focus on the parts that we don't have enough good examples for, and see if we can, you know, get other examples for those types of, you know, notes or patients or language, and in order to build, you know, more robust model that is fair to everyone.
Fantastic. All right. So this brings us almost to the end of this video. So it is now time to discuss what learners will do. Flora, what do we need learners to tell us about? What challenge do we have for them this week?
Okay, so for this week, we came up with a kind of a fun hypothetical scenario where if you can imagine that your hospital has invested in a chatbot system that assists clinicians with the diagnoses. So the underlying model behind this chatbot is the NLP assignment that you just looked at in this NLP model that you looked at in this assignment that can kind of parse medical notes and predict the diagnosis. However, clinicians will access the chatbot via an app on their mobile devices. So they just have to say or read out the SOAP notes, and in real time, the app will provide a diagnosis. You know, it's its best guess, but it will say what it thinks it is. And so what we want you to do this week in your assignment is to kind of write about your experience based on what you've learned in this course. So one example, one question would be, if the Nurses Association has reached out to you to discuss if this app is able to replace clinicians or take their jobs, do you believe that this app is currently able to replace human clinicians? Why or why not? Is that something you can comment on in terms of your clinical experience, as well as the, you know, the performance of this model and what your thoughts are? The second question is, hospital leadership would like your perspective on what risks such an app may carry for the hospital. And so if you remember, we talked, you know, a bit about bias, and I'm sure you have a lot of other perspectives from your experience on what risk an app like this would pose, particularly to your institution that you're from. Number 3 is, how would you explain the role and functionality of such an app to patients? And again, stakeholders are all important, but coming from a clinician perspective versus a patient perspective, that can be very different and have different challenges, and you know, whether or not they would trust an app that's built to do this type of NLP processing. And then finally, number 4 is, do you believe the use of this app to be ethical given all you know about the model? So again, we talked about bias. So very good questions, lots of food for thought. So we're looking forward to hearing your feedback and your evaluation on a model like this.
Thank you, Flora. So we will read every single assignment. So do take a moment and think critically. Don't accept everything that we've said here. Make your own judgment, and let us know by answering the questions in the assignment document. So folks, that brings us to the end of this video. We are week 4 in the program. Stick with us. We are almost at the finish line. It is our absolute pleasure to bring you this program and this course, teaching you about artificial intelligence, particularly in a healthcare setting. My sincerest thanks to the brilliant Flora for all our hard work developing this model, putting together the PowerPoint materials. Thank you, and have a wonderful rest of your day.
Thank you.